Alright guys, let's go over the FRQ portion now. Let's see, number one, metal wire of length 8 centimeters is heated at one end. The table below gives selected values of the temperature T of x in degrees Celsius of the wire x centimeters from the heated end. And the function t is decreasing and differentiable for all x greater than or equal to 0. So basically we have a wire here. They're applying some flames to it. There's my flames. And obviously it's going to be really hot next to the fire, but as you get farther and farther away, the heat decreases. And so that's basically it. So x represents the distance away from where it's heating it. So here's where the source is, and so x represents how far away you are from that source. So that's the story they're telling there. Let's go ahead and look at it. They tell us that it's decreasing and it's differentiable, so that'll be important. All right, part A. Is there a value x on the interval from 0 to 5 at which t prime of x equals -6? Now, whenever they ask you if there is a value on an interval where the derivative equals something, that's MVT. Okay? Justify your answer. So now, this is very important, you guys. I hope you're watching the video. We'll probably mention this as we go, but basically, when you're doing an FRQ, you have to justify that you are allowed to use the MVT first, and then you apply the MVT. Okay? So, what is the requirements for using the MVT? All right. Well, I'll give you a short answer and a long answer. Let's start off with the longer answer. Okay. In class, we said the function has to be continuous on the closed interval. Now, for this particular problem, the interval we're looking at is from 0 to 5. And it would also have to be differentiable on the open interval from 0 to 5. And if that's true, then we can do the MVT. Now, here's the thing. I mean, you can say this. So you could say, since t of x is continuous and differentiable on those intervals, you could say that. But just so you guys know, the short answer is you don't need to say this. The reason why is because something we learned last unit, in Unit 4, if a function is differentiable, it's also continuous. Okay, so you technically don't need to say this, and it could save you some time. However, if you want to say it just to keep that habit in your mind, not a terrible thing to do. So, there it is. So the first thing you guys have to write is, since t of x is differentiable on the interval 0 to 5, we can say t prime of x is equal to, and now we do the whole MVT thing, right? Which is t of 5 minus t of 0 over 5 minus 0 is a true statement. Okay? So since t of x is differentiable on the interval from 0 to 5, we could say t prime of x equals this for some value of t. I'm sorry, some value of x on the interval we just need open brackets here. So there we go. So, since t of x is differentiable on the interval from 0 to 5, we can say t prime of x is equal to this, average rate of change, for some value of x on the interval from 0 to 5. Then what you guys are going to have to do is you're going to have to prove that that average rate of change is what they say it is. They say it should. They say in the problem that it should come out to be -6. So let's see if that's true. So t prime of x is equal to t of 5 would be 70. T of 0 would be 100. 5 minus 0 on the bottom Negative 30 over 5 is negative 6. Boom. We've proven it. So there it is. So this is how I think you guys should be wording it. Okay, I'm going to highlight these things here for you. You should say, since t of x is differentiable on the interval 0 to 5, we can say this little mathematical expression here is true for some value of x on the interval there, and then we need to prove that that does equal negative 6. So all that purple stuff would be good stuff to include. Okay? We have our input variable accounted for, the x, right? It's kind of like when we're doing an interpretation in the context of a word problem, right? You want input and output. So here's my input. You know, we're talking about x and its interval. We're talking about t of x as the thing that's differentiable. And then we're actually looking at the theorem itself. So I would say those are 3 good things to include. Okay? So let's go ahead and take a look at the next one. Now the next one, I'm messing with you here a little bit, but it's on purpose, and yes, it will be on your test. So be ready for it. I lost my place. Let me go back. The question is different, and that is on purpose. Read it carefully. There's a very important difference. Do you guys see what the very important difference is on that one? The very important difference is that I'm not asking for a place where the derivative equals something. I'm asking for a place where the function itself equals something. That's a whole other theorem. Okay, that's the IVT. That's the intermediate value theorem. So yes, I'm being a little bit mean here. I'm asking you guys to remember something from chapter 3. And yes, it will be on your test. And that's because I want you guys to be able to distinguish between a question that asks for a derivative, which is MVT, and something that asks for the original function, which is IVT. Okay? So, is there a value of x on the interval from 0 to 5 for which t of x equals 80? Justify your answer. Okay. So, first of all, this stuff that I'm about ready to do, you don't need to write on your test, but I just want to refresh your brains on what is the intermediate value theorem. The intermediate value theorem basically says that if you go from point A to point B, somewhere along the way, you must have crossed point C, right? And that means that C is in between A and B. Now that actually means that the y value for C is in between the y values for B and A. And it also means that the x value for C is in between the x values for A and B. Okay, so you're thinking of this as a point with an x and a y value, but there it is. So that's basically what the intermediate value theorem states. And this is the one where I kind of just encouraged you guys to memorize a little statement on how to say it. So let's see how we do with that. Let's cover a few other bases though real quick. So first of all, there was a requirement for the IVT. And the requirement is that the function has to be continuous. Okay? So if you have any holes, gaps, or jumps, then it's possible that that one point that we were hoping existed doesn't. So the IVT doesn't work if your function's not continuous on the interval. So we do have a requirement for continuity, and therefore you have to state that. Okay? Now let's go ahead and take a look at it. So we're going from 0 to 5, right? 0 to 5. I'm asking you, is there any place where t of x would have to equal 80? Well, t of x is going from 100 to 70. So if I am at 100, right? Let's draw another graph. I'm way up here at 100. And I go down to 70. At some point along the way, should I have crossed at 80? Yes, I should have. So there's your answer, basically. So the answer to this question is yes. So since this function is continuous, and why is it continuous? Because it's differentiable. So I'll start over. Since this function is continuous, there must be somewhere where the function equals 80 because it goes from 100 to 70, right? Now there's not just one way to word this, but I'll try to stay as close to the way I taught it as possible here. Here's how I taught you guys to say it originally. since t of x is continuous on the interval 0 to 5, and it's got to be a closed interval with brackets, and goes from 100 to 70, there must be some value x such that t of x equals 80 on that interval. There you go. So that's kind of the way I had you guys say it before. So once again, I want to review with you guys real quick before I move on to the next question. If it's a derivative, if they're asking if there's a value where the derivative equals a specific value, that's probably an MVT. The requirement is that it's differentiable, and then you show your formula, okay? If they're asking if there's a value x on an interval for the function, not the derivative, then that's an IVT question. And all that's required is that it's continuous on the interval, and this is how you should be phrasing it, okay? Now, if you don't want to word it just like me, that's fine, but I will tell you that there are a few things that are key here that you need to include. You definitely need to state that it's continuous. T of x is continuous. You need to state that it's continuous on that interval. You do need to state that it goes from 100 to 70. And then obviously you need to state your conclusion somehow that t of x does equal 80 for some value of x there. So however you guys want to say it is fine, but that's the idea. Okay? So let's continue on. So we've looked at IVT, MVT. Let's go ahead and continue on. I've lost my place again. Just a second. All right, part C. Is there a value on the interval from 0 to 5 for which t of x equals 60? Justify your answer. So we're going from 0 to 5 and 100 to 70. Now the answer is no. We can't be sure. That doesn't mean the answer is definitely no, it doesn't equal 60. Well, actually for this problem it would be because it's strictly decreasing. So I'll erase my previous statement there. But we would say no. And here's why. Because if I'm going from 100 at t equals 0, I'm sorry, x equals 0, and then 5 seconds later or whatever, centimeters later, I am at 70, and the problem tells me that t is decreasing only, then it never made it to 60. 60 would be below that 70, right? So that it absolutely could not have equaled 60. Now, if they didn't say it was only decreasing, then here's what could have happened. It could have went down, hit 60 once, hit 60 again, and come back up to 70. But that would mean the function would have to be increasing at some point, right? But it's not. So we can't say that it's increasing anywhere. Therefore, it actually never equaled 60. So what this is this is kind of like using the IVT to prove that a statement is false. Okay? Here's how I would word my answer to this. Since the function is decreasing, I'll put only decreasing on the interval. And t goes from 100 to 70. T could not have been 60. On that interval. Okay, and once again, there's more than one way to word that. So hopefully you guys just understood the explanation. But what are the important components of this explanation? Okay, well, it's decreasing, right? That needed to be said. Once again, we need to emphasize this is all happening on an interval. We also want to include the fact that t only goes from 100 to 70. When I first thought of this, I would have worded the last part a little bit differently. I might have said, well, 60 is not in between 100 and 70. So that's another thing to say. But there you guys have it. So those are good table questions. The first two in particular are extremely common AP questions. The last one I included was just to keep you guys thinking about the things that we are learning here. So I don't remember if there's going to be one like C on your test or not. So I'll just leave that as an open possibility for now. All right. Let's go ahead and take a look at the next one here. So I wonder if it might help you guys more if we did the last one first, because this one is kind of like an application, but of something. It's kind of asking you to look at things from a new perspective, but we've definitely done questions like this. So I think that if we start here, it'll help you understand number 2 better, but you might understand number 2 anyway. I don't know. I think I'm going to go ahead and start here, though. So let's go ahead and start off with Frq number 3 and see if that helps. So f of x is a continuous function. Need to change my thing there. Okay, continuous function. Funny looking interval there, right? They're not including 2 in the interval, but they are including -7. They tell us it's twice differentiable, except at x equals -5. And you can see that in the table. The derivative and the second derivative don't exist at that point. But everywhere else it is twice differentiable. The function and its derivatives have the properties indicated in the table below, and D and E indicates that the derivatives do not exist. All right, so let's go ahead and take a look at this. So part A, identify the interval that corresponds to each description below and justify your answer. So part I, f is concave up and increasing on what interval? Okay, so f is concave up. Let's look at that. F is concave up when f double prime is greater than 0. F is increasing when f prime is positive. So we're looking for a place where f double prime and f prime are both positive. All right, let's take a look here. Right here. As you guys can see, both f prime and f double prime are positive on that interval, and I don't see it happening anywhere else. So my interval is from -2 to -1, and we're going to use open brackets. I'm sorry, open parentheses here because the endpoints are not included. Why are they not included? Because if you include -2 and -1, the derivatives, the second derivative equals 0, and there is no concavity, but we want it to be concave up at that point, right? So we don't include the endpoints when we're talking about concavity or increasing or decreasing. All right, next one. F is concave up. Well, let me erase my stuff here first. F is concave up. Okay, so once again, I'm looking for the second derivative is greater than 0. And decreasing. Okay, so now I want my derivative to be negative. So I want my second derivative to be positive, first derivative to be negative. Here's one. And that's it. There's only one. So that interval is -7 to -5. All right, next one. F is concave down and decreasing on concave down. Second derivative is negative, decreasing. First derivative is negative. So we're looking for double negatives here, and that would be here at 0 to 2. Last one, we're looking for where the second derivative is negative, but the first derivative is positive, and that would be right here and right here. So there's two answers for the last one. So -5 to 2, as well as -1 to 0. Okay, so that's one thing I'll ask you guys to be doing there. Let's go ahead and continue searching questions here. And you guys can see how the points are being distributed as well on here, in case you were curious. Where does f have a relative maximum and minimum? Justify your answers. Okay, so I'm going to show you guys how you should be justifying your answers here. All right, now this one, actually the graph is a little bit easier. But for this one, let's review for a second. A relative max is what happens whenever a derivative goes from positive to negative, left to right. So when your function's slope goes from a positive slope to a negative slope, you end up with a relative max. So if I'm going from positive slope to negative slope, that's a relative max. Relative min is the opposite. If you're going from a negative slope to a positive slope, you end up with a relative minimum. Okay? So basically, I'm looking for at what point, for which values of x, now this is not an interval, I'm looking for a single value of x where the function suddenly switches from positive to negative. And good things to look for are the following. You want to look for anywhere where your function, where the first derivative is either 0, because that's how it would go from positive to negative, or maybe there's a cusp, because that could also go from a positive to a negative and creating a relative max or min. Okay, so we want to look for anywhere where the first derivative is 0, and then we're going to look to the left and right, and that will tell us whether that point is a relative max or a relative min. This is a very important question, by the way, for the AP exam, and I'm going to make it important on your test as well. So make sure you guys know how to do this one. So let's take a look. So the first thing I want to do if I want to find my relative maxes and mins is we're going to start by looking in the f prime column, and I want to find everywhere where it either does not exist or it's 0. So there are 3 places where the derivative does not exist or it equals 0. Now, let's take a look at the first one I have here, D and E. To the left, it's negative. To the right, it's positive. So at x equals 5, my function went from a negative slope to a positive slope, and that's a cusp. Now, how do I know that these two lines are connecting, by the way? Because I told you this was a continuous function, and also because there actually is a y value at that point that this function that they're sharing. So there you go. But anyway, so that means that this one is a relative min. So I would say we have a relative min at x equals -5. Since, and this is my explanation, f prime goes from negative to positive at that point. There you go. That's how you need to answer it. So you get 1 point for identifying it correctly, but 1 point for your explanation as well. So that's 2 points. Okay? So you got to have both of those things. But we're not done. You can only get the points for each one you identify. So we have another one we need to identify here. We also had 2 others. So let's go ahead and find those as well. My other 2 were at 0 here and 0 here. So let's start off with our first 0 on the left side here. The slope on the left of that is positive. The slope on the right of that is positive. That is not a relative max or min because the slope doesn't change. So I will not be including that as one of my answers. Let's take a look at the last one. The last one goes from a positive slope to a negative slope. So we would say we have a relative max at x equals 0 since f prime goes from positive to negative at that point. I'll just put x equals 0. Now, did you guys notice how I almost forgot to put prime there? If I didn't put prime, I would have lost the explanation point. That's very important. F doesn't go from positive to negative. F actually goes from positive to positive, and even if it did go from positive to negative, that doesn't make it a relative max. It's when the derivative goes from positive to negative that makes it a relative max, so it's important that you get that piece correct. So there you guys go. That's how you identify and justify the location of the relative extrema. All right, continuing onwards. Part C, where does F have a point of inflection justify your answer? So before I answer the question, I'm going to rehash some knowledge for you here. What is a point of inflection? A point of inflection is a point where your concavity changes. So if this is a point of inflection, my graph may go from concave up to concave down, or it could also go from concave down to concave up, right? Either way, that's what a point of inflection is. Okay? Now, concavity has to do with the second derivative. Okay? Now, concavity is less picky than relative extrema. With relative extrema, whether it goes from negative to positive or positive to negative actually matters, because that tells you what kind of extrema it is. But with points of inflection, that doesn't matter. It doesn't matter if it goes from positive to negative or negative to positive. So long as it changes, that's a point of inflection. Okay? So we're looking for the places where f double prime equals 0. Now, f double prime is different also than f prime. In this subtle little detail here. So the extra little detail that we need to worry about with our points of inflection is, once again, I am a little not sure about what the expectations are, because I've seen it done in two different ways. But some people believe that a point of inflection, it can't be a cusp. Others believe that it can be. So unless maybe I'm just wrong about something. But for now, I'm not going to put that ambiguity on your test. But I do want to talk about it on our study guide at least. So for now, I want to keep things simple. Let me skip the ambiguity for now, and we'll keep it simple. So here's what I want you guys to know. Unlike the derivative where you look for where it doesn't exist and where it's 0, with our second derivative, let's just say, let's look for the places where it equals 0 only. Okay? So we have one here and we have one here. Now if I look to the left of that, that's negative, and if I look to the right, it's positive. So that means that that is a point of inflection. For the other one here, we're going from positive to negative. So that's another point of inflection. Okay? So we have 2 points of inflection, and that's what I want you guys to be aware of for your answer, and then I'll chat about the one that's ambiguous here. But for now, here's our definite answer. This is all you need to know for your test. There is a point of inflection at x equals -2 and at x equals -1, and that is going to be 1 point for you guys if you just identify the 2 places where it happens. Okay? Then the explanation would be, and it's a little bit simpler, like I said, than the first derivative. Since f double prime changes signs, at those points. And that's good enough. There's no need to specify going from positive to negative or negative to positive, because it doesn't matter. All that matters is that it did in fact change. Okay? So there we go. Now, just for the heck of it, let's, for the sake of your knowledge and pondering, I suppose, let's talk about the other one. What about where the second derivative is undefined? My concavity is still changing. the point still exists. We have an x value and a y value. It's a continuous function, as the problem said, so there's no holes, gaps, or jumps. And in fact, I can draw a picture of this for you. We're at the point x equals -5, y equals -4. So we'll call that -5. We'll call this -4. So I've got a point right down here, basically, right? And my first derivative goes from negative to positive, but it doesn't exist. And this is a continuous function. The only way a derivative can fail to exist on a continuous function if there's a cusp. So basically, it's having a sharp turn there. And it's going from positive double derivative to negative, which means it's going from concave up to concave down. So I have a decreasing function that's concave up at that point, and then I've got a positive slope that would be concave down after that, which would look maybe like this. Now I did my best to try to make that look like a cusp, but we do have a sudden sharp change of turn there. So if I were to accent it a little bit more, maybe we could see it slightly better. I can't really curve back on itself like that, but you get the idea. We have a sharp turn there. So we have no first derivative because it's a cusp, right? But notice that this is a point. The point exists, and the concavity does change. And so I personally don't see a reason why we cannot call that a point of inflection as well. But I've never seen them ask this ambiguous question on the AP exam, so I'm going to go ahead and just ignore it. But I at least want to talk about it with you guys and let you know that there's a point there and the concavity changes. Whether or not you want to call that a point of inflection, I'll leave that up to your judgment there, because honestly, I don't have an answer for why it can't be, but the textbook we use says that it cannot be. All right, let's continue onwards here. So we're now done with number 3. Let's jump back up now and take a look at number 2. So number 2 is actually the same questions pretty much as the questions that we looked at in number 3. But instead of me giving you a table of data, I'm giving you a graph. Okay? So it's literally the same thing. You just have to know how to read the graph as opposed to a table. And we didn't do a whole lot of graph reading in class. I might have assigned a couple like for FRQs, but that's it. So let's take a look at it and see what you guys think. All right, so the graph of f prime, the derivative of f, consists of a semicircle and 3 line segments as shown above. Identify the interval that corresponds to each description below and justify your answer. Now, here's something that we got to pay really close attention to. Okay, this is not a graph of f. This is a graph of f prime. Okay, so that is very important to pay attention to. Now they're asking me questions about f here. Okay, so my graph is of f, but they're asking questions about f. So let's see. Now, f is concave up when the second derivative is positive. But now we have to remember the second derivative is the derivative of the first derivative. In other words, this is the slope of our graph. So f double prime is the slope of the graph that we have. So when is f double prime positive? Anytime this graph that we're looking at has a positive slope. So like for instance, from here to here, f double prime is positive. Why is that? Because this is a graph of f. F double prime is the derivative or slope of this graph. And since this graph has a positive slope, that means f double prime would be positive. Where else is there a positive slope on this graph? How about from here to here? So for those regions right there, I would say that f double prime is positive. Okay? Now, where is f increasing? Well, f, not f prime, but f, let me change my color here. F is increasing whenever f prime is positive. Now, since this is a graph of f, how can you tell where f prime is positive? Well, that would be anywhere where f is above the x-axis, or f prime, I mean. So anywhere where this line is above the x-axis is a place where f prime is greater than 0, and therefore f would be increasing. So here is above the x-axis, here is above the x-axis, and here is above the x-axis. In fact, almost all of it is. Just those two legs on the far left and right are not. So now the question here is asking us two things. When are these two things happening at once? When is it concave up? No, I shouldn't say it. When is f concave up? And when is f increasing? Well, which parts of this line have I highlighted in pink, representing concave up, and green, representing increasing? Well, I see two regions that have both of those things happening, right here and right here. Those are the two regions where f is both increasing and concave up, because f double prime is positive and f prime is also positive. And so what are those intervals then? So I would say this interval, the first one here on the left, is going from -4 to 3, -3. And the other one is from 1 to 2. Okay. Let's go ahead and take a look at another one here. Where is f concave up? Now, we already went through all that talk. F is concave up. I'm using the wrong color there. I want to stick with the same colors. F is concave up when f double prime is positive. F double prime is positive when this graph has a positive slope. So that was here and here, right? Now, where is f concave up and decreasing? Well, f is decreasing when f prime is negative. In other words, when the slope of f is negative, right? Well, when we're looking at a graph of f prime, how can you tell where f prime is negative? That would be where it is below the x-axis. So now we're looking for places where it's below the x-axis. That would be here and here. Now, since the question is asking us to identify the places where those two things are happening simultaneously, I wanted to see where is my pink and hot pink, or whatever the color you want to call it is, where are those overlapping? And that would be here and here. Oh, nope, last one doesn't work because I don't have the other pink on there. So it's just the first one. So only where it goes from -5 to -4. On that interval, f is concave up because f prime has a positive slope, which means f double prime is positive, which means f is concave up. And it's decreasing because f prime is less than 0, because the f prime graph has that portion of the graph being below the x-axis. Okay? So let's go ahead and take a look at another one here. For number 3, where is f concave down? So now I'm going to transition here. Concave down. F is concave down when f double prime is less than 0. F double prime is the slope of f prime, which is the graph we're looking at. So when is the slope of this graph less than 0 or negative? The slope of this graph is less than 0 or negative here because it's sloping downwards, here, and here. So there are 3 regions where the graph is sloping downwards, and therefore on those intervals f double prime would be less than 0. Okay? Now we also want to find where it's decreasing. I think I used hot pink for that earlier. So where is f decreasing? Well, f is decreasing when the first derivative is negative or less than 0. Where is f prime less than 0 on a graph of f prime? Anywhere it's below the x-axis. So that would be here and here. So we would say the only place where both of those things are happening is on the interval from 3 to 4. That's the only place where I have my purple and pink highlighting. All right. Let's see if we can find another one here. Number 4. Now, I haven't been doing my justifications, so I'm going to do my justification for number 4 here. Here we go. Let's see. We had concave down. I think I was using this funny little pink color there. Concave down. Once again, that means the second derivative is less than 0. And for the graph that we're looking at, f double prime is less than 0 as the slope of that function anytime this function is decreasing or going downwards. So f double prime, we've already said earlier, was negative here, here, and here. Now we want to find where is f increasing? Well, f is increasing whenever its derivative is positive. Now, since I'm looking at a graph of the derivative, where is the derivative positive? Anywhere we are above the x-axis. So that would be there, 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 and here. And that's it. And where is their overlap? Here's one big region right here. Now, you guys might be tempted to break it up here, and you wouldn't be wrong if you did, but there's no reason to. We can just say we have concave down and increasing from -3 to 1, and then we can say there's one other region where it's both concave down and increasing, and that would be here. So there's our intervals. So here's how I would word my justification. Ready? Now, your justifications always come back to these statements here. It has to be in terms of this. So it's actually not too bad. You don't have to get really wordy with it. So we would say, for example, on number 5, you get a point for your answer. First of all, my answer would be from -3 to 1, as well as from 2 to 3. And then I would say, here's my reason. Since f double prime is less than 0 and f prime is greater than 0 on those intervals. That's all you have to do. Okay? So the hardest part is actually identifying them. The explanation is not that bad because you're just stating what we state at the very beginning. Okay? So there it is. If you guys want to check your explanations on these other ones, feel free to remind me. I'll show you if you're right or wrong, but basically there it is. Okay, let's continue on here. Where does f have a relative minimum and maximum? Okay, so where does f, not f prime, where does f have a relative min and max? I don't care where this graph has a min or a max. I care where does f have a min or a max. Now, you got to remember, we have a relative max anytime f prime goes from, we said before, positive to negative. Okay? Now, since this is a graph of f prime, it's positive anytime we're above the x-axis. And it's negative anytime we're below the x-axis. Okay? So, where at on this graph does f prime change from positive to negative? Well, there's only one place that happens, and it's right here. At this point, we're going from green, which is positive, to negative, which is negative. So at that point, we have a relative max. So we would say we have a relative max at x equals 3 since f prime goes from positive to negative at that point. Here's your answer. That's one point. Explanation, other point. All right. They also want the relative mins. We said that relative mins happen whenever f prime goes from negative to positive. Now, where does that happen? That happens right here. at this point we have f prime being negative because it's below the x-axis to positive because now it's above the x-axis at that point. So we have a relative min at x equals -4 since f prime goes from positive to negative at that point. Once again, answer is 1 point, explanation is another. This is not multiple choice, mind you, right? You have to come up with these explanations from your own mind there. All right, let's continue onwards. Oops. Last one. For which values of x does f have a point of inflection? Justify your answer. Okay? Where does f have a point of inflection? There is a point of inflection. I've been writing POI a whole lot. I would not do that on your AP exam. We have a point of inflection when f double prime changes signs. Okay? Anytime f double prime changes signs. And we also want to stipulate, well, I'm putting that in a weird place. I'll put and f double prime equals 0. Okay? Now, where does f double prime equal 0 on this graph? Well, remember, what is f double prime on a graph of f prime? We said before many times now, it's the slope of that graph. So where does the slope of this graph equal 0? There's really only one place where that happens, and that's right here. We have a 0 slope tangent line there at that point, right? So there's only one place. So at that point, f double prime equals 0, but it's only a point of inflection if f double prime changes signs. In other words, if the slope changes. Does the slope of this graph change at that point? We're going from a negative slope to a positive slope, and so yes, it does change. So I would say we have a point of inflection. I'm going to rewrite it. Point of inflection at x equals 1 since f double prime equals 0 and changes signs at that point. Now, that's a fine answer, and that's all you really need to know for your test on Friday. However, we have the ambiguous situation again, right? Remember how we were talking about how, well, what about where f double prime is undefined? Is that okay? Look right here. At this point, that's a cusp, so the slope doesn't exist at this point, which means that f double prime doesn't exist at that point. But it still changes. It goes from a positive slope to a negative. So you could argue that it's also a point of inflection at -3 because we're assuming that this is since this is the graph of the derivative and the derivative is continuous, the original function would have to be continuous too. So this point exists on the original function. But is that a point of inflection? Once again, that's open for grabs. I'm not sure. I would not include it just yet. And I'm not going to put anything ambiguous like that on your test tomorrow. But technically, I don't see why x equals -3 wouldn't be a point of inflection also, because that point actually exists on the continuous curve, and the concavity goes from positive to negative. So I'm not too sure why we're going to say no to that, but for now we're just going to leave it out. Okay? All right, and I think that kind of clears up everything. We're hereby done with this one. So the rest of your study time should be devoted to kind of looking over your guys' integral review and the 2 assignments that I gave you guys on my AP. Some of the questions have been slightly altered, but some of them I literally just copied straight from there. So it's kind of worth your while to go back and just kind of peruse those with any time that you guys have remaining. So anyway, we'll see you guys Friday.